equals 0, 1, 0, 0, that means it belongs to class x2. Okay, if you do xj equals 1, 0, 0, 0, then that means it belongs to class 1. Okay, so this is a sparse representation, and it is interesting when you have a small number of classes. But if you have a massive amount of classes, so imagine you're trying to embed a text, and each of these features is a word, and you want to see which words are in the text, and you have a vocabulary of 2,000 words, this becomes very long and very sparse. So it is not ideal for as an input. So what an embedding layer does is you have your embedding matrix, let's call it E, with a fixed size. So let's say if that is the number of examples, let's say you have n examples, n features. So if this goes now until n, so you have n classification targets, or n classification, n categories for classification. You have a matrix of size n, and you have an embedding of size d. So this size is fixed. Normally it would be a lot smaller than the number of categories that you have. So you have 2,000 words. Maybe this is going to be of size 36 or 64 or something like that. And what you have is a set of trainable weights. So let's call this theta 0, 0, theta 0, 1, theta 0, d, and it goes theta n, d, theta n, 0, theta n, d. Okay? And these are all trainable weights. So what your embedding matrix does is you have a lookup table. So now you say, okay, my input feature is category 0. I look for embedding 0 here, and this is now going to be my input to the machine learning algorithm. Some interesting things that you can do, and this is very relevant especially for text, is that if you learn these embeddings properly, then the operations within rows are meaningful. So the word-to-vec example is sort of the clearest example where you can do sort of word association. So if you do France, so you can do some France is to Paris, as Russia is to, and then when you ask this to the embeddings, so if you put this through the embeddings, then you will get Moscow here. You can also do arithmetic operations. So if you do king minus man plus woman, you get something that is very similar to queen. So these become meaningful. So having an embedding layer is quite interesting because you can learn these associations between words. The way they propose to do it here is not to get general embeddings, but put a generic embedding layer here, randomly initialized. So if you have a categorical feature such as demographics, whatever that means, you put it through an embedding layer, and then the embeddings are trained specifically for your training problem. So you learn the optimal representation of the categorical feature for the problem that you are trying to solve. This doesn't mean that they will generalize or that you'll be able to do arithmetics, but you are learning an embedding layer. So this helps generalizing. This helps the model to generalize properly. Okay, and then the learning problem is actually very simple. It's so it's a sigmoid output. If you want, so they do a top K approach. So you get a sigmoid output which says, does this app have to be recommended or not, with a probability, and then you fetch the top 100 probabilities and you recommend those to the user. And what they do is they put a weight on the wide output and a weight on the deep output, plus a bias, and then they do the logistic regression on that. Simple problem, simple architecture, I think. Are there any questions on the architecture? Okay, it's quite straightforward. And then the training is also quite standard. They do backpropagation, and one maybe non-standard thing that they do is that they update the white part using an algorithm called follow the regularized leader, which I didn't have time to look up. Does someone know what follow the regularized leader is? We'll have to look it up. And the deep part, they optimize it using Aradhye, which is an adaptive gradients method. So yeah, all that very standard. The results are, we were discussing before, the results are a bit obscure. I was not very confident, but I mean they show that if you use only the white part, you have so the standard. That's your baseline, which is the algorithm that they were using at the moment. Was a white for recommendation, and then they show a 4% improvement with the wide and deep. And then they also have an offline, they show that offline there is no improvement. So they had a holdout set to test these models. They showed that there was no improvement. They argue that it's because of the continuous learning part. So when they deploy the system in the Google app, in the Google Play Store, they actually receive training data continuously. So the model is constantly adapting itself to new recommendations, new likes, new downloads and whatnot. So they claim that is the reason that they see a statistically significant improvement online, but no improvement offline. We're gonna have to take their word for it. But that is so that is the conclusion of the paper. Is that they so they present this this new this new architecture, which is capable of both memorizing previous examples and generalizing well. So yeah, so we read this short abstract and we said this seems like something that we can possibly test, unlike many papers out there which are very complicated to implement. This one seemed quite simple, so we went ahead and did our own implementation. We applied it on this dataset, which is a wine reviews dataset. It's on Kaggle, so if you guys want to take a look at it, it's a very interesting dataset to practice natural language processing. Basically what you have is 130,000 wine reviews made by professional wine tasters, and you have a bunch of features that come with that. So you have things such as the denomination of the wine, the designation, where it comes from, the description, the points that were given by the taster, price, region, whatever. You have a bunch of features, and there's another data set which has even more columns. So if you want to toy around with machine learning models for natural language processing, this is a good one. The problem that we wanted to try to solve was, can we create a regression on the points based on the description? And can we create a wide and deep model for this? And so the answer is actually that the wide and deep model was not that hard to set up. It's okay. Oh, there's nothing on this side. Okay. Anyway, so what we did, do we have a guy want to? Yeah. I'll try to do that. So what we did was we did some data pre-processing.